Hi all, this is Mr. Yeager for chemistry, and this is our, I think, last video for acids and bases before we move into some of the equilibrium stuff with my class. We are looking at what are called buffers and then the acid-base titration, which the titration is one of the biggest lab activities that we do in a chemistry, high school chemistry course, where you are trying to identify the concentration of an unknown acid or base that we give you. It is the classic kind of chemistry experiment that you see pictures of setups in laboratories and chemistry labs, and it's a very common technique, used in daily business in chemistry world. So anyway, good picture here. We didn't really mention it in any prior video that flowers are an amazing indicator of pH, okay? They actually can change different colors based on the pH of the soil that they are in. And so that is a very common sign of, health and well-being for the soil in that area would be based on what the colors that come out from that soil that go into the color of the plant itself. Again, this presentation made by another wonderful chemistry teacher, always trying to make sure that they know they get credit for it, okay? So here we go. Oh, sorry. Starting off slowly. All right. A couple terms, though, that we, want to mention, we don't necessarily use a lot, is something called a buffer, okay? This is big if you do start getting into like college level chemistry. You'll do a ton of stuff with buffers, okay? But a buffer is a substance, like it says, that will resist a change in pH, okay? As the name is implying it, you start adding acid or you start adding base, and if you don't have a buffer, the pH will change fairly dramatically. It'll change fairly quickly, okay? But with a buffer, you can keep on adding the acid and base, and again, like it says, in limited amounts. You're not dumping a ton in, but in limited amounts, it will resist that change in pH for a period of time or a period of volume that you add. Eventually, you do overcome it, and then you'll see a spike that occurs, but it is something that helps slow it down. So again, these are very good things to have. Obviously, you see here buffers are in lakes and blood naturally to help make sure that if you do put something in your body or you do get chemicals in the lake, that they are able to absorb those and kind of still maintain the natural habitat of the lake or the good health in your own body with your blood, okay? But that's where, again, if you overdo it or something bad, you kind of shock your system or shock the lake, that can cause a big damage in the ecosystem or, again, your health. Other examples where we purposefully use buffers would be cleaning products, shampoos and stuff. They're meant to obviously help you resist some attacks on your hair if you're talking about shampoo, lotions with your skin, medications, and then if you happen to have a fish tank or something, you put buffers in so that as the fish poop and other things happen in that fish tank, that you are able to maintain still good health in it, and obviously you still have to go in and clean, but it's able to manage those changes in pH levels, very gradually. All right. We also break acids and bases into two types. You've heard me kind of say strong a few times. I've never said the weak acid or base, but we do need to be able to discern between strong and weak. Strong is any sort of acid or base that will basically completely dissociate, in other words, completely split into its ions when you add them, versus a weak acid or base where you put it in solution and it only partially breaks up. So this is like related with some solubility things sometimes, but it's the idea that it doesn't immediately ionize, it doesn't immediately split up, okay? In neutralization reactions, we basically have been saying everything is strong, and then when we've been doing the Bronsted-Lowry reactions, we've been doing weak examples. Okay, weak acids and base examples. All right, so that's where, like we said, with the Bronsted-Lowry, where like the reaction's going both directions, that's where you will see it go one way, but some of it is making it go back the opposite way. So it's not all going one direction. Indicators, mentioned this with the litmus paper, okay? They're going to be used in these situations called titrations, which we're going to identify what they are next slide. But indicators are, again, some sort of chemical that is used that can help, that will change colors based on what the pH is. So you have a ton of examples here. You have litmus right in the middle, and you can see it's either red, pink on one side and purple on the other. Other ones can have some slightly different colors occur. A lot of them mainly are one color or the other. We do have something called a universal indicator that can change many colors, okay? Again, it's not perfect. You know, we'd be like, oh, that's orange, but then at 5, it's also slightly orange. But you can at least get maybe a little bit more technical with where the pH is versus something like methyl violet. Well, it has 3 different colors. 2 of those colors only occur at less than or near 1, and then it's always violet or purple the rest of the time. So that would be a little bit tougher. We do choose the indicator based on where we want the solution to end with the pH. So I would use methyl violet if I'm like, I want it to be at 1 pH and I get that blue color. Okay, so there is use to all of them. These are the things that are in some plants and why plants have different colors to them as well. All right. So I guess going a little bit more, again, litmus paper is a good beginning test of just going, is it acid or base? Okay, that's really all it is. It's not going to tell you what the pH is. It's not going to tell you whether it's, I mean, it'll tell you, hey, it's blue, so that means it's greater than 7. That's all it will tell you. Okay, red, it's less than 7. So litmus is like a very good initial test to be like, ooh, this is acid. Do I want it to be acidic? You know, etc. pH paper, that's another one that we do use in the classroom. This uses the universal indicator, and so this obviously can get it a little bit closer, okay? So you can see that you could try to discern it out between 1 through 14. Some of them it's going to be a little close. I mean, if you look at 12 and 13 on the picture, they're basically almost the same identical color. So how do you tell between that? How do you tell between some of these yellows? All right. So again, there takes a little bit of, you know, estimation to go on with some of those too. All right, that leads us to titration, okay? So as I already said, this is a technique to identify the concentration of an unknown solution of acid or base, okay? So we do it where we do know the volume and concentration of the other substance. So it's always an acid, well, we will be doing it always with acid and base. There are other types of titrations out there. We're going to do only acid-base titration. So the idea would be, you know the concentration of the base, and you put a fixed volume of base in there. So you know the molarity and the volume. You're then going to slowly add the acid, which you don't know the concentration of, and you're going to keep adding it until you reach a neutralization. Okay, so an indicator will tell you when you have reached completion, and what we're trying to do is we're trying to have equal amounts of moles of acid and base, so then we can set up an equation to say that those two things are equal. Okay, so this is your setup. This is, let's see what we have here. Yep, so you have your solution that you're going to be using. Okay, the unknown solution is going to be in the flask. Okay, that would be our Erlenmeyer flask. So we do usually use the solution that we know. We're going to put it in what we call a burette. I'm going to go to this one. This thing right here is called a burette. Sometimes it's written this way, and sometimes we get fancy and add a lot more T's. Okay, so that would be what we're looking for. So you put the standard solution in the burette. You put your unknown solution, standard meaning known, and then you put your unknown solution in the Erlenmeyer flask, and what we're going to, and then we add an indicator on in here. Okay, and as we add the standard solution in, we get to a point where it just changed color, and now we know the volume. So we know the molarity of the standard solution, and we know the volume of the standard solution, and we already know the volume of the unknown solution. Okay. So there's only one thing we're missing, which is molarity, and you're going to see it looks very similar to a formula you've seen before. These create what are called titration curves, and these are very, very specific types of curves, and there's a very clear trend to how these work, okay? But they'll show you how the pH changes over time. All right, we call them an S curve, okay? Because what will happen is you'll add a little bit of acid or base, and over time you'll see it slowly change, and then when you get really close to the point where you're at neutralization, it spikes past that point. Because the idea is, if you keep adding past this 7 point, there's no acid anymore, and so immediately the base takes over the solution, and that's why it shoots up, or vice versa if you're doing base to acid. So the only thing would probably be on these to recognize whether you're doing acid to base or base to acid. Basically look at what you're starting with. So if you're down at the bottom, obviously you have acid, and then the base must be being added. This one you're starting with base, and then acid is occurring, so you're adding acid. All right. The point in the curve where it's most vertical, we call that the equivalence point. And the equivalence point is where the amount of acid, the moles of acid equals the moles of the base. That they have completely canceled each other out, and all you have left, if you're doing a strong acid and base, would be water. Now, if you do have a weak acid and a strong base, or a weak base and a strong acid, that equivalence point can be somewhere else, okay? If you're using a strong base, it'll be above 7. If you're using a strong acid, it'll be below 7 with a weak base. So it does depend on what you're using. We primarily will, when we do a lab, we're going to be doing strong acid, strong base. So if we actually graphed it, we'd get some sort of graph that looks like that. So the titration equation. This looks very similar to the dilution equation. Whoop. Okay? Except now we do MAVA. So molarity of acid times volume of acid times the particles of hydrogen. In other words, how many hydrogens are in your acid chemical, or how many hydroxides are in your base. So it's MAVA equals MBVB, but then we add in, or not add in, we have to multiply in how many hydrogens are being given and how many OH minuses are being given based on the chemical formula. So if you have H2SO4, you're going to put in a 2 for NH+. If you have NaOH, that's only 1. So NOH minus would be just 1. So it just depends on what the chemicals are that you have involved with it. Okay? So let's do an example here. So, again, reading for context, getting our formulas right. Okay, so my formula is MAVA times NH plus equals MBVB NOH minus. Okay? All right, it says I have 42.5 milliliters of 1.3 molar KOH. So these two things are together. KOH is my base because it's OH minus. So this would be my VB, this would be my MB. KOH only has one OH minus. So therefore, my NOH minus factor will just be 1. It's being neutralized by 50 milliliters of H2SO4. So this is my VA. H2SO4 has 2 H's, so my NH plus factor is equal to 2. It says find the molarity of the acid. So I'm solving for MA. So I have MA times VA, 50, times NH plus is 2, equals MB is 1.3 times 42.5 times 1. Solve for MA. So 1.3 times 42.5 times 1 is 55.25. I'm going to then divide that by 100. 50 times 2. My molarity should come out to 0.55. 2 sig figs because the 1.3. I never use the factors. I don't use the number that I'm using for the N. So 0.55 molar would be the molarity of the acid. If it takes 45 milliliters of 1 molar NaOH. So once again, this is all about my base. So VB, MB, and OH, there's only one, so MB is equal to 1. 57 milliliters of HCl, so this is my VA, and H is only equal to 1. I wanted my MA, is what I'm looking for, so I'm setting this up again the same way. MA times 57 times 1 equals 1 times 45 times 1. So 45 divided by 57, pretty easy one here. I get 2 sig figs. Molarity of my acid will be 0.79 molar. All right, last one to do together. If it takes 67 milliliters, 0.5 molar H2SO4. So I'm finally starting with my acid. So I have VA, MA, and I have 2 H's, so 8N is equal to 2. Down at the bottom, I have 15 milliliters, so I have VB and OH3, so I have 3, N is equal to 3. And I want my molarity of the base. So this one I'm doing 0.500 times 67 times 2 equals molarity of my base times 15 times 3. So 0.5 times 67 times 2, okay, divided by 45, 15 times 3. Molarity of my base, 2 sig figs, 1.5, I'll write that better, 1.5 molar. Okay. That's the idea. Okay. I'm not going to do that last one. We got it. Very good. Thank you.